Okay, we're happy to have Yash Lodha talk about finitely presented simple groups in the homeomorphism group of the Rills.
So thank you so much, Professor Bowen, for the invitation. It's a great pleasure to give a talk in this seminar. And I would like to talk about finitely presented simple groups in this talk, in particular, ones that act on the line by orientation-preserving homeomorphisms. So the three sort of terms in the title of the talk that you see, finitely presented, simple, and homeomorphisms of the real line, are sort of fundamental terms in modern group theory. So let me start with the second one, simplicity. So simple groups, in a sense, are fundamental objects. One can think of them as building blocks, although, to be honest, this is a little bit misleading. So the point is that for finite groups, they indeed are building blocks, because a corollary of the Jordan-Holder theorem says that every finite group admits a unique, up to isomorphism type of the simple composition factors, composition series. So if G is a finite group, then you have this sort of sequence of normal subgroups such that each successive quotient is simple. And these quotients, so you can have another composition series, but these quotients will remain as a set, as a multi-set, the same. And the point is that somehow every finite group is built out of these simple groups, these finite simple groups, in a sort of a unique way. However, this doesn't hold for infinite groups, not even for the integers. So this idea is a little bit misleading for infinite groups. However, simple groups are still in infinite group theory, in geometric group theory, widely regarded as fundamental objects. And understanding the landscape of simple groups is a worthwhile pursuit that a lot of us have found very interesting. And simple groups show up all over in geometric group theory. So you know, this notion is a bit fundamental. So a fundamental question, though, is, do there even exist finitely presented infinite simple groups? Yeah. So a group is finitely presented if it admits a finite presentation, finitely many generators and finitely many relations. Can such a group be infinite and simple? So this question was answered in 1965 by Richard Thompson, who discovered the first examples. Let me start with the first example he discovered, was Thompson's group T. This is the group of orientation preserving piecewise linear homeomorphisms of the circle, which I identify as R mod Z, which satisfy the following properties. The slopes, whenever they exist, are integer powers of 2, and the breakpoints, where the derivative is not defined, lie in Z adjoint half, the dyadic rationals mod Z. And of course, the set of this dyadic rationals mod Z is preserved. So you take this, you define this group as all such piecewise linear homeomorphisms of the circle. It's easy to check that each of these properties is preserved under composition and inversion. So this indeed forms a group. And you can sit down and build by hand lots of such piecewise linear homeomorphisms and really convince yourself that this is an interesting group. It has lots of elements. But what's surprising is that it's finitely presented and simple. Yeah. The famous Thompson's group F, which I'm sure you may have heard of in talks, and especially the amenability of this group is a major open problem. This is the stabilizer of 0 in T. So T acts on the circle, which I identify as R mod Z. And so you have the point 0 on the circle. And if you take the stabilizer of that point, that is exactly Thompson's group F. F, however, is not simple. It admits an infinite abelianization. It's famous for other reasons. It's not famous for being simple, because it's not. A related example is Thompson's group V, which is defined similarly, but discontinuities are allowed. In effect, V acts naturally on the Cantor space by homeomorphisms. Okay. So let me just summarize. So Thomson discovered three groups in 1965, F, T, and V. T and V were the first examples of finitely presented infinite simple groups. F, however, is not simple, has an infinite abelianization, is famous for other reasons. For instance, it's a major open problem whether it is an amenable group. It's an interesting candidate because it does not contain non-abelian free subgroups. However, it's not elementary amenable. It does not satisfy a non-trivial law. So it has all kinds of unusual properties. And these three groups have had a major impact on modern geometric group theory. There are hundreds of papers that have been written about them. And they are kind of go-to candidates for, if you're looking for counterexamples to conjectures, then you sort of go to one of these groups and try and check your hypothesis against one of these examples. Now, these examples have been generalized a lot. I'm mentioning only a few names, but really there's a whole industry of generalizations of these examples, starting with Higman, and then Ken Brown, Stein, Brin, Clary, Rover, Nekrashevich. They're all kinds of directions of generalizations. The caveat is that all of these groups contain torsion, including T and V. Yeah, so T and V contain torsion, and all of the subsequent generalizations contain torsion. In 1998, Berger and Moses discovered the first examples of finitely presented simple groups that are torsion-free. Yeah, so torsion freeness was sort of mysterious for a long time. Can there exist finitely presented simple groups that do not contain torsion? And Berger and Moses solved this problem by uncovering certain lattices in products of automorphism groups of trees. So if you have a tree, say you have a finite valence infinite tree, and you take all its automorphisms, that's a very natural locally compact group. And if you take a product of two such automorphism groups, then in that product you have lattices. And some of these lattices surprisingly turn out to be finitely presented, torsion-free, and simple. And then Capras and Remy in the 2000s discovered certain lattices in products of automorphism groups of buildings, which are finitely presented and simple. However, these lattices always contain torsion. Yeah. So this is pretty much the landscape of finitely presented simple groups that has been known until now. You have sort of the Thomson world. And I would like to remark that the Rover-Nekrashevich generalizations actually were quite interesting because they turned out to have very interesting finiteness properties. And so a remarkable theorem due to Witzel, Zaremsky, and Skipper says that, in fact, these Rover-Nekrashevich theorem, the Rover-Nekrashevich groups have very interesting finiteness properties. So they're interesting for that other reason. But what you're looking at on the slides is sort of so far what's known in the landscape of finitely presented simple groups. Only one family so far was known of finitely presented torsion-free simple groups. That was the Berger-Moses family. So one of my long-term projects is to understand examples of finitely generated and finitely presented simple groups, especially ones that admit interesting actions on manifolds of low dimension as well as the Cantor space. So started off with a question a few years ago. So this is an old question of Remtulla from 1980. And it was asked by many people over the years, including Derwan, Navas, Rivas, Clay, Rolfson. It was in the Kurovka notebook as well. By the way, any questions up until so far? I think I went too fast. I have a tendency of going really fast when I use slides.
Yeah.
I have a question, but it may not be answerable quickly. What is a non-positively curved building?
So that's a whole another. So I really don't want to get into that. I'm sorry.
That's all right. I can't.
Really like I'm not going to use that at all in my talk. So that's just think of that as just a source of examples.
So
that's a source of examples of. It's not non-positively curved in the sense of a non-positively curved cube complex, for instance. But I don't want to get into that.
It's about,
So
these
yes,
are
there's another
boundaries of higher rank groups of some type?
Yes, I think so. Yeah. Yes, there's another person asking the question.
Yeah, can I ask a
Olga?
question? Could you go
Yeah.
to the previous slide?
Yes.
So you said that the group T is defined on a circle, but the group V is defined similarly, but on a Cantor set. How do you get the
Yes.
Cantor set? Is it
Right,
an
so that's a
inverse
really
limit
good
or
question.
something?
So the point is that you allow discontinuities. So what you do is you take the orbit of discontinuities, which is exactly the dyadic rationals, and you do a sort of a blow-up construction. So you replace each point by an interval, and then at the end of this, you get another circle and another action of the same group on the circle, but this time you have an invariant minimal Cantor set inside. And so you restrict the action to that Cantor set, and that's the action of V on the Cantor set. So you sort of build it up from the circle itself. But there's also a very natural external definition using tree diagrams.
You kind of add limit points. You compactify.
You blow up points. So there are two ways of looking at it. So one way of looking at it is you start with the action on the circle. Now V doesn't really act on the circle, right? Because there are discontinuity points that are allowed. So how do you deal with that? So one way of dealing with that is you take the orbit of discontinuity points, you blow them up. So you replace each point by an interval of smaller and smaller length, so that the sum of the lengths is say 1. And then you get another circle, a larger circle, and you have your action on this larger circle, which is no longer minimal. So the complement of these intervals is going to be your Cantor space, and the restriction to the Cantor space of the action is still faithful action of your group on the Cantor space. But a much more natural way to do this is
you end up with a Denjois action or something like that?
Something like that. Yeah, you are exactly. You're doing that kind of a thing. Yeah, exactly.
Okay, and maybe one more question. So one half is not really important here. You can check 1 over P.
Yeah, so that's exactly one of the generalizations of Higman. You can replace 2 by n for any natural number n bigger than 1. Yeah.
Okay, thanks.
Sure. Yeah. So going back to this question, so this old question: do there exist finitely generated infinite simple groups of homeomorphisms of the real line? So this is sort of a nice, like, cute question, and this was not. It was open for a while because there weren't really that many examples, right? So Thompson-like groups can basically never be examples because they're the ones that act on the line are locally indicable. So in particular, they admit a non-trivial homomorphism onto the integers. And there are some other obstructions like Thurston stability theorem and the Vitti-Morris theorem. And so this problem, like, I was quite interested in for a long time. Me and my co-author, we found a solution. But before I tell you the solution, let me tell you a very cute algebraic characterization of when a countable group G admits a faithful action by orientation preserving homeomorphisms on the real line. This admits a very cute algebraic characterization. Such an action exists if and only if the group is left orderable. So if there is a total order on the group such that the order is left multiplication invariant. So for every triple, if f is less than g, then hf is less than hg. Yeah. So a countable group acts on the real line by orientation preserving homeomorphisms if and only if such an invariant total order exists. It's very nice. And actually in higher dimensions, it's completely mysterious. For example, is there such an algebraic characterization for countable groups to act on the plane? That is something that is completely mysterious. In fact, we don't even know an example of a torsion-free countable group that cannot act on the plane by orientation preserving homeomorphisms. As far as I'm aware, that's a major open problem. So dimension 1 is somehow nice in this setting, and so you can kind of, there's the algebraic side of the theory where you can study orders on groups, and there's sort of the more topological, dynamical side where you really work with concrete actions on the line. So that also makes this question kind of appealing. And so we answered this question in 2019. We showed that, Hyde and I showed that there exists continuum many up to isomorphism, finitely generated simple groups that act faithfully on the line by orientation preserving homeomorphisms. Subsequently, Matebon and Tristino provided a more dynamical generalization of our construction as groups of piecewise linear homeomorphisms of flows. So what they did was really cute. They sort of understood the combinatorics of our going into our construction, and they kind of turned it into a very nice dynamical framework. So I'll actually tell you what they did more than what we did, because what we did will take much longer to explain. So what they do is that they take the Cantor space and a minimal homeomorphism of the Cantor space, and then they build a mapping torus. So you take the Cantor space, cross the interval, and then you glue both ends via this homeomorphism. And then you take the group of all homeomorphisms of this object, of this mapping torus, which are piecewise linear in the sense that for every point, you have a kind of a decomposition of some interval times, interval times interval, so that, open set in the Cantor set times interval, so that the restriction of the homeomorphism to that is along the flow lines is Thompson-like. So it's sort of like the definition I gave you here. So the slopes, whenever they exist, are integer powers of 2, and the breakpoints line dyadic rationals, and so if you make that kind of a construction, then it turns out that under the right if you choose the right homeomorphism of the Cantor set, then you get a finitely generated simple group. Our construction is much more combinatorial. We found ways of encoding 2 different actions of subgroups of Thompson's group F on the line by some combinatorial mechanism, which we call a quasi-periodic labeling, and it gets a bit technical, so I don't want to talk about that. In any case, this talk is about finitely presented examples, so completely different from these ones. But just for historical note, I just mentioned this. And then in a subsequent paper with Hyde and Rivas, we actually found a very elementary example, which was, in hindsight, it was like, wow, we wish we had found this example before. So elementary to define. To prove that it works is hard, but to define it's quite elementary. So you can take the group T, which I defined as a group of homeomorphisms of the circle, and you lift it to the real line. So if you have a group acting on the circle, then because the real line is the universal cover of the circle, you can lift these homeomorphisms as homeomorphisms of the real line, which commute with integer translations, and define a group that is generated by all of these homeomorphisms. And that's called the lift of this. This group is called T bar, and it has the structure of a central extension of T, where the kernel is Z, and this Z consists of integer translations. This is a very nice group. This lift of T group I'm just going to call it T bar in this talk. So this T bar group is quite nice, and it was first mentioned in the paper of Gis and Sergescu from the 80s. Now, the lift I chose here was, well, I identify the circle as R mod Z, right? I go from the real line to the circle by modding out by Z. But I don't have to mod out by Z. I can mod out by lambda Z for some lambda bigger than 0, which is irrational. Yeah? So I can define an alternative lift where my map now is R mod lambda Z for some lambda bigger than 0, any lambda bigger than 0. And I get an alternative lift, which is T bar lambda. So it's the same group. It's the same isomorphism type, but the action is different. Yeah? This, for example, the T bar lambda commutes with integer multiples of lambda, translations by integer multiples of lambda. Now, what if I take these 2 groups and generate a group? What if I take T bar and T bar lambda? Both of these groups are isomorphic, but as actions, they are different, right? So if I take these 2 actions and generate a group, it turns out that group is simple if lambda is irrational. So maybe I'll just quickly summarize, because I think I went over it really fast. So you have the group, yeah.
Why is it when you take those 2 groups, which seem to be rather they make different because you're really rescaling by lambda.
Yeah.
Why when you take the group they generate, isn't it just a big old crazy free group?
So first of all, it cannot be free because it contains T bar, which has tons of
Yeah, I don't
relations,
really
right?
mean free, but it looks like a
But
star
you mean like
product.
a free product or something like that, right?
That's
Like,
right.
yeah. Right. I mean, it's very easy to see immediately that it's not a free product because you have translation by one and translation by lambda in there. So those commute. That's the z square. But anyways, but to show, but the fact that it's true that the fact that they're simple is kind of surprising. And the reason is that if you pick an element in this group, the normal closure actually intersects with both of these copies of T bar. And to see that there is a dynamical argument that goes into it, that in fact, this is the case. But I know what you mean, that when you first look at it, it almost feels like this should be some sort of free product. But there is a non-trivial interaction of somehow slopes and breakpoints that creates enough space for commuting relations to occur. And those commuting relations in turn and provide this mechanism for checking that in fact the normal closure of every element is the whole group. So yeah, like I see what
Okay,
you're saying,
I mean,
but it's a sort of,
so there's
it's
a
sort of a
dynamical
funny
ingredient
thing.
there. Yeah.
Yes, absolutely. So yeah, like let me just quickly go over it because I think I talked too fast. So you start with the group T, which acts on the circle. Yeah, very kind of nice group, piecewise linear, slopes are powers of 2, breakpoints are dyadic rationals. You lift it to the real line. So you take each homeomorphism in the group, you choose a lift to the real line. Now, of course, you have many choices of such lifts. You take all of them. So you take all lifts of all elements and you generate a group, right? Now, this group is a group of homeomorphisms of the real line. This group we call T bar, yeah? And T bar admits this very nice structure as an extension with quotient T and kernel integer translations. But this particular T bar, the lift I chose was coming from R mod Z. I can choose another lift, which comes from R mod lambda Z. And I just take these two lifts and generate a group, and voila, it turns out that group is simple. Of course, it's finitely generated because both of these groups are finitely presented. But this group is not finitely presentable. The group of mine with Hyde from 2019, which I haven't really defined in this talk, is also, none of these examples are finitely presentable because they're all non-trivial limits in the Gregorchik space of Mark groups. And finitely presented simple groups are isolated points in the Gregorchik space of Mark groups. And also Matebol and Tristino's examples are not finitely presented, yeah? So none of these examples are finitely presentable. And so, okay, so we answered this question and there were all these new constructions and, it was a satisfying endeavor, but there was still like this lingering dissatisfaction that there is no finitely presented example. And, for a long time, we thought that maybe such examples just don't exist. Like if a finitely presented group acts on the real line by homeomorphisms and it's simple, then that group must be like Z mod 2Z. So just like, you flip the real line along 0 like that. That's it. That's the only example maybe. Because somehow all of these examples seem to be non-trivial limits in the Gregorchik space of Mark groups. But in the winter, just a few months ago, we had been speculating over an example for a while and we were trying to perturb it for many years. And we discussed a certain perturbation that seemed to work, and then we just spent 2 months doing nothing but that, and we realized that it actually does work. So let me tell you the example, which was very exciting that we found this. So the question is, do there exist finitely presented infinite simple groups of homeomorphisms of the real line? Now, of course, such groups, if they exist, also have to be torsion-free, yeah? Because if you act by orientation-preserving homeomorphisms on the real line, you have to be torsion-free. In fact, you're left orderable, which is even stronger. And so these are like another family of finitely presented simple torsion-free groups since the Berger-Moses groups, but in fact, they also act on the line, so that makes them even more interesting. It's not known whether the Berger-Moses groups act on the line. They probably don't, in my opinion, because of all the stuff that Brown, Fisher, and Hurtado did with high-rank lattices, and Derwan and Hurtado showed recently that high-rank lattices cannot act on the line by homeomorphisms. And so I have a suspicion that somehow that machinery might be deployed to show that Berger-Moses groups also cannot act on the line. So in that sense, these groups are and these groups also have some very different properties than the Berger-Moses groups. But anyways, let me tell you the definition. So the following is recent joint work with Hyde. It appeared on the archive in February. For each natural number n bigger than 1, we define gamma n as follows. So it's a group of homeomorphisms of the line which satisfy the following. So they're piecewise linear homeomorphisms of the line with a discrete set of breakpoints. So a breakpoint is a point where the left and the right derivative does not coincide. Yeah. So now we are allowing a countable discrete set of breakpoints. In previous examples, like in FT and V, you had finitely many breakpoints. Here, you're allowing countably many breakpoints. But these breakpoints must lie in Z adjoint 1 over n times n plus 1. Yeah. Each of these homeomorphisms must commute with the translation t goes to t plus 1. And then the third condition is a little bit funny, but I'll explain to you why it's kind of natural. So for each point x in the reals where the derivative is defined, there exist I and j and z such that the derivative is n to the I times n plus 1 to the j, where the difference I minus j is how many integers you have crossed in the positive direction as you move from left to right. And if it's negative, then it's how many integers you've crossed in the other direction as you've moved along. Yeah. So let me just try to give you like an intuitive explanation of this bullet point. So imagine that you're a tiny ant living on the real line, and you can only see locally in a very small neighborhood what's happening. Yeah. So if a homeomorphism is applied, then you notice that your tiny little world gets stretched by some factor, yeah, or it gets squeezed by some factor. So there's some slope. And that slope is n to the I times n plus 1 to the j, yeah? Now, if you're living in some integer interval, n plus 1, and the homeomorphism keeps you inside that interval, then the slope gets changed by a factor of some power of n times n plus 1, yeah? So you see a change in slope of n times n plus 1 raised to the power some number, yeah. But if you pass an integer, then you have a factor of n more than a factor of n plus 1. So your slope increases by a positive factor of n, and it could also increase or decrease by some factor of n times n plus 1. Yeah. And if you go in the other direction, then you reduce a factor of n, but also you could have a factor of n times n plus 1. So it's sort of like you are keeping track of both of these numbers, and as you pass integer points, you gain. It's kind of a battle between n and n plus 1. Yeah. If you stay within your integer interval, n plus 1, or sorry, I shouldn't say n plus 1. I should say it's j plus 1. So j is an integer, j plus 1. You stay within that interval, then your slope changes by a factor of n times n plus 1 to some integer. I'll explain this in more detail on the iPad when I get to that. But I hope that at least it sort of makes sense, this bullet point, that your powers are being sort of monitored by, they're correlated with how many integers you've passed as you move along, as you apply one by one your homeomorphism.
Yash, let me ask you just a basic question. So
yes.
On this bullet point 3, where you have x dot f prime, are you...
Right, that's the derivative.
So you mean F prime evaluated at X?
Yes,
So you,
yes.
okay. So
Yeah,
this
yeah,
is just
sorry,
the
that
derivative.
should not be. Yeah, this is a bad notation for a derivative. But I mean, yeah, it's just the derivative. I'm sorry.
Okay, and
I
X,
don't know why I wrote
okay.
that. I should
And
have
then
put a
at,
bracket X. Yeah.
for 3.1, the X dot F is F of X.
Exactly. Yeah. So
Okay.
usually, so my notation, I like write actions in my papers.
Oh,
So
okay, I
like
see.
to
Okay, then
use
it
X
makes
dot
sense.
F and yeah. I just prefer write actions because yeah. Anyways, so I'll explain bullet point number 3 more when we get to the screen share on the iPad. For now, you should think of it as the derivative is correlated with this combinatorial kind of count of how many integers you've passed as you've moved along. Yeah. And so our main theorem concerns the derived subgroup of this group. And the theorem is that for each n, the group Qn is finitely presented, and it's a simple group of homeomorphisms of the real line. In fact, the group is type F infinity, which is sort of a much stronger property than being finitely presented. So it's a fundamental group of a connected aspherical CW complex with finitely many cells in each dimension. Yeah. So there are these like topological generalizations of finite generation and finite presentability. So the classical finiteness properties are finite generation and finite presentability. And there's an old paper of CDC Wall that generalized these in a topological sense. That what if I take a K pi 1, what if I take a CW complex whose fundamental group is my group, and it's aspherical? So this is unique up to homotopy type. Can I find one with the sort of the smallest possible cells in various dimensions? And if you can find one with finitely many cells in all dimensions, then your group is type F infinity. If you can find one that's finite, then actually the group is type F, and that's a much stronger property. But already type F infinity is strictly stronger than finite presentability. So these are the first examples of F infinity groups that act on the line and are simple. Before I go to the iPad, I'll just mention a couple of applications of our theorem beyond just the sort of curiosity. Let's find finitely presented simple groups in different settings. Let's, because the landscape of finitely presented infinite simple groups is so poorly understood that itself is a worthwhile kind of direction. But also there are some other applications of this. Brown and Gagan in 1984 proved the following theorem, that Thompson's group F is a torsion-free type F infinity group with infinite dimension. So any K pi 1 must be infinite dimensional. And this was surprising because the people thought that all 3 properties should not somehow simultaneously hold for a group. Torsion-free type F infinity and infinite dimensional. Generally, torsion was the reason why you're infinite dimensional for some type of infinity group. And so this theorem was considerably generalized by many authors. So you'll find tons of papers on the archive over the past few decades that prove such and such Thompson groups, such and such generalized Thompson groups have property type of infinity, and they're all infinite cohomological dimension and torsion-free and so on. But no example was found that is simple, right? So the examples of Berger and Moses, they admitted 2-dimensional classifying space. So they do not have infinite dimension. They're very much finite dimensional. So our construction provides the first simple examples of a Brown-Gagan type group. There exists type F infinity torsion-free simple groups with infinite dimension. The proof that they have infinite dimension is completely obvious. They contain infinite direct sums of copies of Z, and hence they have infinite dimension, because infinite direct sums of copies of Z have an infinite dimension, and the dimension of the group is bounded below by that of its subgroups. There's a rainbow outside, so wow, that's this was one of the applications that we thought was interesting. Another application has to do with this notion of commutator width. So if you're a bit more algebraically minded, then if you're given a perfect group, you might ask yourself that does it have finite or infinite commutator width? So a perfect group is a group whose abelianization is trivial. So every element is a product of commutators. Yeah. It has infinite commutator width if for each natural number n, there is an element f in the group which cannot be expressed as a product of fewer than n commutators. Yeah. And so there was an old problem in the Kurovka notebook. Can there exist a finitely presented simple group with infinite commutator width? Yeah. So this problem was solved, and the only known solutions so far are the examples of Capras and Remy, the ones that appear as lattices and products of certain buildings, as demonstrated by Capras and Fujiwara in 2008, but they contain torsion. So these are finitely presented simple groups with infinite commutator width. So they solve the problem, but they contain torsion. So the question is, can there be torsion-free such groups? And the Berger-Moses groups do not admit quasi-morphisms. So our groups do. So there exists finitely presented simple torsion-free groups with infinite commutator width. And the proof is very simple. Our groups admit a very natural, non-trivial homogeneous quasi-morphism, which is given as follows. I just let you look at that. It's a very simple definition. You just take the limit as f goes to infinity of 0 times f to the m. Again, I'm using right actions over n.
This is basically like the translation number.
Translation number, exactly, exactly. This is a translation number, exactly, because the group the whole action commutes with a translation by 1. So you can this is a well-defined number for each group element, and it's easy to check that this is a homogeneous quasi-morphism. And because the group admits a homogeneous quasi-morphism, it cannot have finite commutator width. Otherwise, any non-trivial homogeneous quasi-morphism, actually there cannot be one, because the fact that a commutator can only move so much by this quasi-morphism, I mean, can only move 0 so much by the quasi-morphism. Every product is every element is sort of a n-fold product for some n of such commutators that would contradict the fact that this is unbounded. Yeah. So these are just a couple of applications of our construction that are sort of interesting. That there's on the one hand, they provide the first examples of simple Brown-Gagan groups. On the other hand, they provide the first torsion-free solutions to this whole question. And they just provide some nice examples of finitely presented simple groups, which are substantially different from the Berger-Moses examples. And they sort of live within this world of Richard Thompson, right? They kind of have this Thompson-esque flavor, and so that's the end of my slide show. Now I will share screen on the iPad and try to explain to you what. So how do I? Okay, stop share. And then I will share screen here, but first let me open notes. Any questions? We can take a 2-second break and just okay, I'll just open those. Screen share.
So I guess I have a general question while you're setting up. These results are all algebra. Are they? Do you consider your results from dynamics? Or are they from algebra?
Why make this distinction?